Hello friends, in this video I am going to explain to you the construction of an AVL search tree so that we can just apply the process of insertion, the different processes of insertion, the different cases of insertion in AVL search tree which warrants different types of rotations, and we'll apply those different types of rotations in the course of the construction of the AVL search tree. So it is nothing but a step-by-step construction of an AVL search tree given from a set of data. A set of data values will be given to us, and we'll just take one by one from that data set and construct the AVL search tree from the data values given in that set of data. So I will just take an example to show you how the entire process works, and let me just take an example to show you how the construction of AVL search tree is done. So let me take a set of data values like suppose 64, 1, 44, suppose it is 14, 26, 13, 110, 98, 85. So these are some values which we are given. So from these values we are going to construct an AVL search tree. And how to construct an AVL search tree from this set of data values, I will just show it to you step by step. And each of the step will take the insertion process into consideration, and we will have to apply the necessary rotations which need to be performed in some of the cases, or it might be that in some of the cases the rotations are not necessary because it will not destroy the property of the AVL search tree. So in those cases the insertion will be done in a very normal manner, and there will be no necessary operations which needs to be performed in those cases. But in some cases we need to perform the necessary rotations in order to retain the balance factor, in order to retain the very characteristic of the AVL search tree. So first I will just start with the value 64, then I will insert 1 and 14 and so on until we get an AVL search tree which is completely in all respect will go to fulfill all the conditions of the AVL search tree. So we will just take in step 1, we will take this 64, and in step 1, suppose step 1, we will just insert 64. So insertion of 64 means before the insertion of 64 the AVL search tree was an empty AVL search tree because it did not contain any sort of nodes. Now the AVL search tree will go on to contain one node, and this insertion of one node will be a very simple sort of insertion which will not which doesn't need any sort of necessary operations or rotations which are to be performed, because the balance factor of this node can be easily seen to be 0 because it has no left subtree, it has no right subtree. The height of the left subtree and right subtrees are 0. So 0 minus 0 gives you 0. So the balance factor is 0, which is inside the permissible range of the balance factors which need to be there in the AVL search tree. So this is a quite simple insertion. We will just simply insert 64, and then I will take this 1. We will just do it sequentially according to the values which are given. So step 2 will require us to insert this 1 to the existent AVL search tree in the step 1, that is 64. So we will compare this 1 with this 64 and see that 1 is less than the value 64. So it will definitely go to the left subtree, and we'll just since the left subtree is empty, we'll just link that node containing the value 1 with the node containing the value 64 as the left child of the node containing the value 64. So we are going to insert this 1 in this manner. So step 2 will give us an AVL search tree in this manner. So this 64 and this 1 is on the left subtree of 64. So let us just calculate the balance factors. The balance factors of this leaf node is definitely 0. The balance factor of this node is 1 minus 0 means 1. So this is also a very simple case of insertion, because it needs no further rotations to be performed in order to make it balanced. So it is already balanced. Step 3. Step 3 means we have to insert this 14. So what will be the AVL search tree look like after the insertion of 14? Let me see. So say 14 is less than 64. So it will go to the left side, left subtree of 64. We'll go on to compare 14 with 1 and see that 14 is greater than 1. So 14 will be placed on the right subtree of the node containing the value 1. So it will look like this: 64, 1, 14. So now see, we have the AVL search tree as shown in this figure. So I have to calculate the balance factors yet again, and see this leaf node has a balance factor of 0. This node has a balance factor of 0 minus 1 means minus 1, and this node has a balance factor of what? This node has a balance factor of 2 minus 0 means 2. So we see that a violation of the balance factor has occurred in this step 3. So this needs this needs a rotation to be performed in order to balance the AVL search tree. So how to do that? Let me just apply the rotations, necessary rotation which need to be performed in this case. So we will just see that where the new node has been inserted. The new node is nothing but the node containing the value 14. So this is the new node which has been inserted, and this node, from this node we will go on to backtrack to the root node until we first encounter a balance factor which violates the permissible range of values. So we'll start from here. This is well and good, the balance factor is 0. This is also well and good as the balance factor is minus 1. We'll go to this node and see that the balance factor is violating the very spirit of the AVL search tree. So this should be considered to be the node A, and see that what is in what position this 14 has been inserted with respect to this node A. See this with respect to this node A, this has been inserted, this node has been inserted on the right subtree of the left subtree of node A. So this 14 has been inserted on the right subtree of the left subtree of node A. So right subtree of the left subtree of node A means we have to perform the LR rotations. That is, if the case is like this, that the newly inserted node is on the right subtree of the left subtree of node A, then we should perform the LR rotation. LR rotation is nothing but a double rotation, and that consists of an RR rotation followed by an LL rotation, and RR rotation should be applied to this portion starting from this 1, and the LR and LL rotation should be performed on the entire tree. So we will first perform the RR rotation like this. We will perform the RR part on this part. RR means we have to pull this 14 like this in this anti-clockwise manner, so that this 14 comes over here. So 64 will remain over here, 14 will come over here, and this 14 will come over here, and this 1 will go towards the left of 14. So this is the RR part which we have done. So after that we need to perform the LL with respect to A. So A is this one. So we have to perform the LL with respect to the entire tree, with respect to this A. So we will pull this left child of 64 from the left side in a clockwise manner, so that 14 comes to the root position and 64 goes to the right child of goes as the right child of 14, and 1 will remain as the left child of 14. So this will look like this. After the rotation is performed, LL rotation is performed, 14 will come over here, this will be 1 and this will be 64. So let us calculate the balance factors over here. Balance factor is 0 for this because it is a leaf node, it is also a leaf node 0. So this balance factor is 1 minus 1 means 0. So we see that it is an AVL search tree because all the balance factors are within the permissible range. So this is the ultimate figure which we get in the step 3 after the insertion of the 14 data and after applying the LR rotation. So this 2 rotations is nothing but equivalent to the LR rotation. So this LR rotation gives us this AVL search tree. After this we need to again try and insert this 26 and see what happens. So step 4 means we will insert 26. So 26 will be inserted in what way? 26 is greater than 14, it will come to this right portion, right subtree, and 64 is greater than 26. So 26 will be on the left subtree of this 64. So we will get like this 14, 1, 64 and 26 like this. And see the balance factors, calculate the balance factors once again. This is 0, this is 1 minus 0 is 1, this is 0, this is 1 minus 2 means minus 1. See the balance factors are all well and good. So this is an AVL search tree. We need not perform any sort of rotations to balance the tree because it is already in a balanced mode. So it is already balanced. Step 5 will require us to insert the value 13. So this 13 will be inserted to this AVL search tree and let us see what happens. 13 is less than 14. So it will go to this side. 13 will be a part of the left subtree. So this 13 is more than 1. So 13 will be on the right subtree of 1. So it will look like this 14, 1, 13 and this is 64. This is 26. So let us calculate the balance factors once again. This is 0, this is 0, this is 1 minus 0 means 1, this is 0 minus 1 means minus 1, this is 2 minus 2 means 0. So it is evident that this AVL search tree is a proper AVL search tree because all the balance factors are lying within the permissible range. So we need not perform any rotation in this step also. After this we go to this insertion of 110. So after insertion of 110, let me see what happens. So step 5, so we will just rub this portion for creating some space to do this. So excuse me for rubbing this portion. So this step 6 is insertion of 110. So 110 is greater than 14. So it will come to the right subtree. 64, 110 is greater than 64. It will come on the right subtree and be linked with this 64. And it will look like this. The tree will look like this. The tree will look like this. 14, 1, 13, 64, on the left subtree of 64 is 26, on the right subtree this 110 will be inserted. So we have to calculate the balance factors yet again. The balance factors of all the leaf nodes should be 0 and the balance factor of this 64 is 1 minus 1, that is also 0. Balance factor of this node containing the data value 1 is 0 minus 1 means minus 1. This one is 2 minus 3, 2 minus 2 rather, sorry, because 1, 2, 1, 2, yes, 2 minus 2 means 0. So balance factor, we see all the balance factors are lying within the permissible range of values. There is no need of any sort of rotations in this step because the AVL tree is in a balanced situation. So step 7, in which we can see that we have to insert this 98. So how to insert this 98? 14. 98 is greater than 14, greater than 64, but less than 110. So 98 will be inserted to the left subtree, on the left subtree of 110. So it will look like this: 14, 1, 13. This will be 64. This is 26. This is 110, and this will be 98. So we have to calculate the balance factors once again. Balance factor of a leaf node is 0. Balance factor of a leaf node is 0. Balance factor of a leaf node is 0. This balance factor is 1 minus 0 means 1. This balance factor is 1 minus 2. 1 minus 2 means minus 1. This balance factor is 0 minus 1 means minus 1, and this balance factor is 2 minus 1, 2, 3. So 2 minus 3 is minus 1. So we see that all the balance factors are lying within the permissible range of values. So this is also a balanced, this is also in a balanced situation. So we need not perform any sort of rotations in order to make the tree balanced. So after this we need to insert this 85. So this 85 is to be inserted now in the step 8. So we will just create some space over here to and rub off a little bit of portion over here in order to cater for the remaining step. So step 8. So step 8, I think it is step 8, yes, step 8. So step 8 we have to insert this 85. So 85 will be inserted in what manner? In a normal manner, that is 14, greater than 14 is 85. So we will go to this right subtree. 64 is less than 85. So we will go to this portion. 110 is greater than 85. So 85 will definitely go to the left subtree of 110, and this 98 is greater than 85. So 85 will go to the left subtree of 98. So it will be inserted somewhere over here. So step 8 will give us a situation like this: 14, 1, 13, this is 64, this is 26, this is 110, this is 98, this is 85. So in this situation we again have to calculate the balance factor. So this is a leaf node, balance factor is definitely 0, this is 0, this is 0 minus 1 means minus 1, this is 0 because it is a leaf node, this is 1 minus 3, that is minus 2, and this is an interesting situation because we see that the value is minus 2, which is not inside the permissible range of the values of balance factors which need to be in place for the AVL tree, for the AVL search tree. So this 98 has a balance factor of 1 minus 0, that is 1. 110 has a balance factor of, it is very interesting because it is 2 minus 0 is 2. So we see yet another violation of balance factor in the node containing the data value 110. We will see this once again. The only node which remains to be calculated, the balance factor of the only node which remains to be calculated is the balance factor of the node containing the value 14 is 2 minus 1, 2, 3, 4. 2 minus 1, 2, 3, 4. So it is minus 2. So this is also violating the permissible range of values. So now what we will see that the newly inserted node is 85. The new node is 85. New node is the node containing the value 85, which needs to be seen that in which part it has been inserted with respect to a node which we will first encounter in the course of backtracking from the newly inserted node towards the root, and see the first node which we encounter which has the balance factor which violates the permissible range of values. So that node where we first encountered the balance factor violating the permissible range of values should be considered to be the node A, and with respect to node A we will have to see where this 85 has been inserted. So we will start backtracking from here. We see this is well and good because the balance factor is 0. This is 98, balance factor is 1, well and good. We go to this and see the balance factor is 2, where we see the balance factor is not according to our expectations for an AVL tree. So this is to be considered as the A, because we first encounter this node in the backtracking sequence. So here we see that this 85 is inserted on the left subtree of node A. So see, this 85 is inserted on the left subtree of node A. So this requires a rotation which is LL rotation, that is a single rotation which is called the LL rotation, and that LL rotation is needs to be performed with respect to the node A. So what to do for LL rotation? We'll perform the LL rotation by pulling this 98 in such a way in an anti-clockwise manner so as to place the 98 where this 110 resides now, and 110 will go to become the right child of 98, and 85 will remain as the left child of 98. So the tree will look after the LL rotation. After the LL rotation is performed, the tree will look like this. I will draw the tree over here. 14, 1, 13, 64, 26. This 98 will take the place of 110. 110 will go to this side, and this 85 will remain as the left child of 98, 85. So this is the construction which we have done now after the insertion, after the LL rotation has been performed. So let us calculate the balance factors yet again. So the balance factor of this leaf node is 0, this leaf node is 0, this is a leaf node, balance factor is 0, this is a leaf node, the balance factor is 0, the balance factor of this 1 is 0 minus 1, that is minus 1, the balance factor of this one 64 is 1 minus 2, that is minus 1, the balance factor of this 14 is 2 minus 1, 2, 3, 3 is maximum, 2 minus 3 means minus 1, and see that all the balance factors are within the permissible range of values. So this is an AVL search tree, perfect AVL search tree, where the balance factors are lying within the permissible range of values. So from here we can see that after performing the LL rotation, we see that the AVL search tree is completely in the manner as it is expected by us. So we get, after the insertion of 85, this is the final AVL search tree which we get, and this is the final AVL search tree which we needed to find by the sequence of these values given in the question. So this is our solution, AVL search tree. So if you have any doubts and queries pertaining to this entire explanation of the construction of an AVL search tree from a set of data values, you can well post your doubts and queries into the comment section below so that I can address them. Thanks for watching this video.